This video was sponsored by PostHog. If I told you that computer processors have special instructions that can shift the binary contents of your variables, you'd probably think that's something you'd never need to do. But today, we're going to take a quick look at how CPUs perform bit shift operations and why you've actually been using them all along, without even realizing it. Hi friends, my name is George, and this is CoreDumped. Shifting bits inside a register, either to the right or to the left, isn't particularly difficult to implement. All we need are a few flip-flops. For those unfamiliar, in electronics there are two main ways to implement memory: latches and flip-flops. There are several types of each, but today we'll focus on D-latches and D-flip-flops. A latch is very simple. It's designed to hold a single bit of information, reflected on its output Q. A D-latch has two inputs: a data input and an enable input. When the enable signal is off, the value passed to the data input doesn't matter. The stored value won't change. The only way to rewrite the latch's content is to set the enable signal to 1 while applying the desired input value in the data input. So, a latch can be seen as a memory cell capable of storing one bit of information. A flip-flop is similar to a latch. It also stores one bit. In fact, internally it's built using a latch. The key difference is that flip-flops include a special component called an edge detector, connected to the enable signal of the internal latch. As I explained in a previous video, an edge detector takes an input signal, like a clock, and produces a very short pulse whenever that signal changes from 0 to 1 or from 1 to 0, depending on the type of edge detector. A flip-flop might receive a clock signal that stays high for a considerable amount of time. However, since the enable signal of the internal latch is driven by the edge detector's output, the actual window for writing data is reduced to just the instant of the rising edge. As a result, the flip-flop only captures the value present at its data input at the precise moment the signal transitions from 0 to 1. After that, it doesn't matter if the clock stays high, any value on the data input will be ignored. The edge has already occurred, so the flip-flop won't overwrite its value until the next rising edge. In short, while latches are level-triggered, flip-flops are edge-triggered. Flip-flops are extremely useful because once you start combining them, you can create all sorts of interesting behaviors. In a previous episode, for example, we connected a few JK flip-flops to build a circuit that took a clock signal and reduced its frequency by half with each stage, effectively creating a binary counter. Now let's look at another configuration using D flip-flops. What happens if we connect several flip-flops so that the Q output of one becomes the D input of the next, while they all share the same clock signal? Well, the only way to load data into the system is through the D input of the first flip-flop. After that, each clock tick causes the value to shift to the next flip-flop in the chain. Some of you might be wondering, once we input a value into the first flip-flop, why doesn't it immediately propagate through all the others, making them all end up with the same value? That's exactly what would happen if this circuit were made of regular latches. But remember, flip-flops are edge-triggered. Each clock tick makes them overwrite their stored value with whatever they're receiving at the data input at the precise moment of the rising edge. Once they update their output to this new value, the rising edge is already gone. So even though the clock signal stays high for a short time afterward, nothing else will change until the next rising edge. If you think about it, this circuit can be used as an 8-bit register. A shift register is a type of digital circuit built using a cascade of flip-flops, where the output of one flip-flop is connected to the input of the next. They all share a single clock signal, which causes the data stored in the system to shift from one location to the next with each clock pulse. And that's precisely the behavior we want. If we load this register with binary data, we can shift those bits in one direction simply by waiting for each clock cycle. With a bit of extra logic, we can make our circuit even more versatile, allowing each flip-flop to overwrite its content with the value stored in the flip-flop on its right or on its left. A bidirectional shift register can toggle its shifting direction, so we can move all bits to the right or to the left whenever we need to. More advanced designs even allow parallel read and write operations. Parallel input is especially useful because it lets us load multiple bits, say 8 bits, into the register in a single clock cycle. While one input toggles the shift direction, another input switches between write mode and shift mode. I know some of you like to pause these kinds of slides to analyze every wire, and some of you might be wondering, why keep a serial input and output if we can already read and write in parallel? That's a great question, and we'll come back to it later, so keep it in mind. For now, let's try to answer how is any of this useful when we write programs. But before that, a quick message from PostHog. I have to say, as a non-native English speaker, every time I hear the word hog, I immediately think of these guys. Or their cool upgraded version. But you know what else is cool? PostHog's website. I mean, just look at this beautiful user interface. With PostHog, you can track how users actually interact with your web or mobile app, from the tiniest click to full session replays, feature launches, and everything in between. You get access to an incredible set of tools. Session Replay lets you see exactly how users navigate your product. Feature flags and A/B tests help you roll out new or improved features with confidence. And their analytics suite brings it all together. Events, retention, product trends, everything. All in one place. PostHog is open source, but also cloud-ready with generous free tiers, so you can get started fast. So if you're building a digital product and want full visibility into your users, plus faster feature delivery, PostHog is a game changer. I'll leave a link in the description so you can check it out yourself. I'd really appreciate if you let them know CoreDumped sent you. And now, back to the video. All general-purpose programming languages support bit shift operations. They usually let us take a variable and shift its bits either to the left or to the right. The second operand specifies how many positions the bits inside the variable should move. Deep inside our CPU, there's circuitry made up of flip-flops and shift registers. Every processor provides a set of bitwise instructions, and bit shift operations are a special subset of them. These instructions are incredibly important because they let us load any kind of data into a register and shift it in any direction we want, as many times as we need, regardless of what that data represents. Before we dive into why this is useful, notice something. When binary data is shifted in any direction, an empty bit appears on one end, and a bit is pushed out on the other. Ideally, we should be able to control what gets written into that empty bit, and even retrieve the bit that gets pushed out. So if you were wondering why a parallel in, parallel out register still needs a serial input and output, it's because if we want to shift data in any direction, the serial input tells the circuit how to fill the register during the shift. The serial output is also important because the bit being pushed out might be needed elsewhere. For example, instead of filling with ones or zeros, we could feed back the bit that was just pushed out, creating what's known as a circular or round shift operation. And this is where the usefulness of these seemingly strange operations starts to appear. Imagine we have a string in memory, and we apply a left round shift to all its characters. By doing this, we're essentially replacing each character with another. If that sounds confusing, let's look at the ASCII table. Take the lowercase letter I. If we perform a left round shift on its bits, the resulting bit pattern no longer represents the letter I. It now maps to character number 180 in the table, which happens to be the acute accent character. That's why all the I's in our original string turned into acute accent symbols. If we print the result, we'll see a bunch of random or meaningless characters. But if we know how the original text was shifted, and we reverse the process, we recover the original message. If that sounds familiar, it's because this is the basic idea behind encryption. Now, please don't encrypt data like this in your projects. This is an extremely simple and really bad example of encryption. Always use proper encryption libraries. Modern encryption algorithms are far more complex, but I'm showing this example because it demonstrates how bit shift operations play a key role in cryptography. If you explore any open source encryption library, you'll find bit shift operations everywhere. Another situation where bit shifting is useful is when we want to speed up mathematical operations. Let's take a simple example using the decimal system. Suppose we want to multiply a number by 10. Normally, we would multiply each digit and then sum the results. But if you think about it, we can achieve the same result by shifting all digits one position to the left and filling the empty space with a 0. In decimal, shifting digits to the left and filling with zeros is equivalent to multiplying by 10. In binary, shifting bits to the left and filling with zeros is equivalent to multiplying by 2. That means we can keep shifting left, effectively multiplying the original number by 4, 8, 16, 32, and so on. In the same way that shifting decimal digits to the right is equivalent to dividing by 10, shifting binary digits to the right and filling with 0 is equivalent to dividing by 2. Now, I know what many of you are thinking. Modern CPUs already have single instruction multiply and divide operations, so why would we write code in this obscure way if it takes the same number of instructions? Well, here's the thing. A single instruction doesn't necessarily mean a single clock cycle. When we use a CPU's multiplication or division instruction, the number of cycles depends on the operands, and it can take dozens of cycles. By contrast, a bit shift instruction, regardless of the operand, always takes just one clock cycle. That's the performance benefit. Of course, this method only works when multiplying or dividing by powers of 2. That's just how binary works. So if you're multiplying by 3, for instance, you'll still need to use the multiplication instruction. For the record, I'm not telling you to start manually replacing multiplications and divisions with bit shifts every time you can. Modern compilers are already very good at detecting these kinds of situations during optimization, and chances are your CPU is sophisticated enough to handle it at the silicon level. Even if the compiler emits a regular arithmetic instruction, the processor might internally execute it as a bit shift operation. In the past, however, this kind of micro-optimization could definitely make a difference. Here's an excellent video I recommend watching. That being said, there are many architectures out there, and it's not impossible to find situations where knowing this can actually give you an advantage. For example, in the world of embedded systems, or when working with microcontrollers. And even if you never have to do it manually, you're still using bit shift operations all the time. You just don't realize it because of the countless layers of abstraction built on top of them. In general, bit shift operations play a fundamental role in many areas of computer science. We'll eventually explore those topics in more depth, but for now, let's wrap things up. If you feel like this video should have been longer, don't worry. A dedicated episode on bitwise operations is coming soon. The main goal of this video was to explain how flip-flops power bit shift operations. And by the way, another episode on how they help synchronize everything inside a computer is also on the way. So make sure to subscribe. You won't want to miss it. Thanks to PostHog for sponsoring this episode. Don't forget to check them out in the description. And if you enjoyed this video or learned something new, please hit that like button. It's free and it really helps the channel. See you in the next one.